Hi there, everyone. Today we are going to talk a little bit about equilibrium, and then we're going to talk about rotational inertia and how that's going to end up affecting our rotational mechanics. So, first, let's start with equilibrium. Equilibrium is something that we've actually already talked about, but equilibrium is the state of physical balance. In this state, all opposing internal forces and interactions are equal. Okay. So that is your definition of what equilibrium is. Now, you have different conditions of equilibrium, though. In equilibrium, the internal net force of the system is going to be equal to zero. So for static equilibrium exists when there is no motion at all. Dynamic equilibrium exists when there is constant motion. So those are our two different situations where we have equilibrium. We have static equilibrium. Static means not moving, okay? And then dynamic means it's moving, but there's a constant velocity. But here's my question for you. Do all instances of F net equals zero result in equilibrium? So in this case, we have equilibrium and you have a force going to the left and a force going to the right, and therefore your net force equals zero. But sometimes you can have a net force equal to zero, but those forces are not going to end up giving you equilibrium because you're going to end up having rotation. So if you've ever held a hockey stick, or even you could probably do this with a golf club because it's got that club foot on the bottom of it. But if you had two forces going, if they're not acting at the exact right spot, you're going to end up having some kind of rotation. So in this case, you're going to have a clockwise rotation. But because you have rotational acceleration, you do not have equilibrium, okay? But you do have your net force equals to zero. So that brings us to a second condition of equilibrium. Our second condition of equilibrium, you need to have your torque is going to be equal to zero. Your sum of all torques are going to be equal to zero. So in equilibrium, an object will not have angular acceleration. So our first situation, we don't have linear acceleration. And in our second situation of equilibrium, we don't have angular acceleration. So when we're looking at angular acceleration, what causes angular acceleration? So something that we talked about in our last video is the difference between linear or translational values and then rotational values. So when we're talking about force, our force is our linear or our translational value, whereas our torque is our rotational force. And we know that force equals mass times acceleration. So a force is going to cause an object to accelerate. So it makes sense that a torque is going to cause an object to rotate, to accelerate rotationally. Okay, so talking about torque, just a quick review from yesterday. Torque is equal to your radius times your force times sine theta, because you want to make sure that that radius and that force are perpendicular to each other. Your sine theta is your angle between the applied force and the direction and the direction of the pivot. So now here's a great example, and this example is going to really apply to your lab for today because you're going to be looking at, it's called balancing act, and you're going to look at how do you balance things. So in this situation, the two children shown are balanced on a seesaw of negligible mass, meaning that we're not going to pay attention to the mass of the seesaw. The first child has a mass of 26 kilograms and sits 1.6 meters from the pivot point. If the second child has a mass of 32 kilograms, how far is she going to be from the pivot point? Okay, so let's think about this for a second. When we're looking at that, we know because I don't have rotational acceleration, I know that my sum of my torques in my clockwise direction is equal to the sum of my torques in my counterclockwise direction. Now you might be asking, how the heck did you know that? Well, here's the deal. My sum of my torques is equal to zero. My sum of torque is equal to 0. Why is that? Because there's no angular acceleration. And what are my torques? Well, I have my sum of my torque, and the weight of this girl right here is going to cause a clockwise rotation. So that's going to be a clockwise torque. And the boy right here is going to counterbalance that and is going to be a counterclockwise torque. So you have to pick one as positive and one as negative. So your sum of your torques are the torque clockwise minus the torque counterclockwise. And in this case, I only have one clockwise and one counterclockwise. So I don't need to designate if that's the torque of the girl plus the board or whatever. Okay. So when I'm looking at this, I need to think of my sum of my torques clockwise equals the sum of the torques counterclockwise. Well, what is torque? Torque is going to be your radius of, we're going to call this the radius of the girl times the force. And the force of the girl is going to be the weight of the girl, or the mass times gravity of the girl, is equal to the radius of the boy times the weight of the boy. Okay, so when I look at that, I know that the first child is going to be, we'll say the first child is the boy. So the first child sits 1.6 meters. So 1.60 meters times the weight, and the weight is 26.0 kilograms times 9.8 meters per second squared. And in your lab, you can go ahead and use 10 for your weight or for your gravity. And then that's going to be equal to the radius of the girl, or the radius of the girl, which, so this is the radius of the boy, and this is the mass of the boy. Okay, the radius of the girl, because that's what we don't know, times the mass of the girl, which is 32.0 kilograms, times my 9.8 meters per second squared. So my gravity is going to actually end up canceling on both sides. And I'm going to go ahead and do 1.60 times 26 divided by 32. Okay, and that's going to end up giving me the radius that the girl is sitting at. So that value is going to be 1.3. So the radius of the girl is going to be 1.30 meters. Now the question, it says, what is the FP, the supporting force exerted by the pivot? Well, if you think about it, what are our forces? So we have our board, and we have the weight of the girl. We have the weight of the boy. And because it's in equilibrium, we have the force of the pivot going up, and the force of the pivot is going to balance that. So my sum of my forces in my XY direction is going to be equal to 0. And that's going to be equal to the weight of the girl plus the weight of the boy minus the force of the pivot. So the force of the pivot is going to be equal to the weight of the girl plus the weight of the boy. So if I just went ahead and used 10 for this, that's going to end up giving me 260 plus 320. So 320 plus 260. And I'm just rounding this for the sake of this problem to be able to do it really quickly. And that's going to end up giving me 580 newtons is the force that needs to be pushed up to be applied by the pivot. So this is a perfect example of equilibrium. Now, we're not really covering too much equilibrium right now in this unit because we're going to cover it over time over the next few months, but that is something that I want you to see. We have rotational equilibrium and we have translational equilibrium. So what have we learned so far? We've learned that torque is a force that causes rotational motion. We've also learned that the same torque can be produced by a larger force with a shorter lever arm, as with if you have a smaller force with a larger lever arm, you can end up getting the same torque there. Okay, so your torque is dependent on your radius, your lever arm, and the force that's being applied. When balanced torques act on an object, the object is in rotational equilibrium, and the sum of your torques equals 0. Now, from your reading, something that we've learned is the center of mass of an object follows all of the laws of motion. And that's something that we actually covered last unit. We talked about in our lessons. And then also, an object will rotate around the center of mass if torque is applied. So the object is going to rotate around the center of mass. That's where your axis of rotation is going to be. So here's an example problem for you. And you'll notice I jumped ahead to in-class practice problem number 26. So you're going to have to flip your pages to that. But the reason I did this is because I think it really applies to your lab that you're doing today. So it says right here, students hang heavy masses from a 2-kilogram rod and attempt to balance it on a pivot point under its center. So if it's under its center, okay, this is going to be the pivot point. And if it's under the center, the 2-kilogram rod, the center of mass is at that point, okay? And it says a pivot point under its center. If a 5-kilogram mass is hung on the rod at a distance of 23 centimeters from the center, where should the 7.2-kilogram mass be hung on the other side to balance out the rod? So we end up having here, we have 23 centimeters or 0.23 meters. And we have a 5-kilogram mass. So we have 5 kilograms times 9.8 meters per second squared. That's going to be the force going down. Then we need to figure out what our x value is. Okay, our x value is going to be for a 7.2 kilogram mass times 9.8. Okay, and for it to be able to balance. So if it's going to balance, that means that the sum of my torques equals 0. This one is going to be my clockwise torque. This one is going to be my counterclockwise torque. So I know my sum of my torques equals my torque clockwise minus my torque counterclockwise. So they're going to end up being equal to each other. So we end up having that our torque clockwise equals our torque counterclockwise. Okay, so what are our torques equal to? Well, we have our clockwise is going to be 7.2 times 9.8 times my radius, that's what we don't know, is equal to 5 kilograms times 9.8 times a distance of 0.23 meters. And when I go ahead and calculate that out, I end up getting that my distance is 0.16 meters or 16 centimeters. Okay. Now, the question is, does that make sense? And it does, because you want to have your lever arm shorter because you have a much higher mass, right? So it makes sense that your 16 centimeters is going to be smaller than your 23 centimeters. So there's another thing that we need to talk about when we're talking about torque, because we know force equals mass times acceleration, and that's in our linear values. So what if we're not talking about linear, we're talking about rotational? So we need to talk about rotational inertia. When we're dealing with something that's rotating, we're dealing with many points that have different masses, right? And so we have linear or straight line inertia, and that's an object's tendency to resist change in linear motion, okay? Whereas then we have rotational inertia. Rotational inertia, or that's designated as I, rotational inertia, okay? Whereas straight line inertia is designated by your M, your mass, okay? A rotational inertia is an object's resistance to change in rotational motion. So if you have a large I, that means an object is really difficult to accelerate, okay? So how hard is it to accelerate something rotationally? This depends on the mass, and it depends on how far the mass is distributed from the axis. So most often we end up using two of these rotational inertias. We end up using the most I equals mr squared and I equals 1/2 mr squared. Now your rotational inertias are going to be provided for you in your textbook, and you do not need to remember all of your rotational inertias, okay? You don't need to remember them by heart, but you should know that the rotational inertia for a point mass, the rotational inertia for a point mass or a point is equal to mr squared. Okay, that is one that you should know. But again, your moments of inertia are provided for you in your textbook, and you're not going to be expected to memorize all of your moments of inertia. So here's a sample question for you. 4 particles, each with a mass of 3 kilograms, are placed at the corners of a rectangle, as shown below, and held in place with a lightweight rod. Calculate the moment of inertia for the rigid object about the axis shown. So this is your axis. So you could spin it this way or you could spin it the other way, but you're spinning around that. So imagine you have a rod, and on that rod you have a box that's spinning around it, okay? And so when I'm looking at that, I want to figure out what is my moment of inertia or my rotational inertia. My moment of inertia is the sum of the inertias of each of my point masses. Okay, so that's going to be equal to I1 plus I2 plus I3 plus I4, because we have our 4 different masses. So this is, say, 1, mass 2, mass 3, and mass 4. Okay, so when I'm looking at this, I have my rotational inertia for number 1, and each of them is 3 kilograms. So number 1 is 3 kilograms, and my radius is my 1 centimeter. So that's going to be 0.01 squared plus 2. 2 is going to be right here. So 2 is going to be 3 kilograms times 0.04 squared. Then I have 3. 3 is going to be 3 kilograms times 0.04 squared. And then finally, I have number 4, which is 3 kilograms times 0.01 squared. And when I add those together, I end up getting that my moment of inertia or my rotational inertia for this system is 0.0102 kilograms times meters squared. Okay. So moving on to our next question, we have a 5 kilogram solid sphere, a 5 kilogram solid disc, I apologize, has its mass distributed uniformly and is free to rotate about an axis through its center. Okay, so you have your solid disc and you have rotation about the center right there. Okay. And so if you have rotation about the center right there, then it says it's free to rotate around the axis through its center if the diameter of the disk is 42 centimeters. So going to the diameter of the disk, you have a radius is going to end up being, so your radius equals 0.21 meters. Calculate the rotational inertia. So when I'm dealing with the rotational inertia of a disk, that is going to be equal to 1/2 mr squared. So to find the rotational inertia here, I have 1/2 times 5 kilograms times r squared, and r is 0.21 squared. That's going to end up giving me a rotational inertia here of 0.1103 kilograms times meters squared. Okay. So just to go over some of this information, we have force and torque because we're going to start looking at second law for rotation. So we're looking at Newton's second law, but we're going to deal with rotation. So we know Newton's second law, sum of forces equals mass times acceleration. So how do we equate that to torque? Okay, how do we equate that to torque? Well, when we're dealing with mass times acceleration, the rotational equivalence for mass is I, and the rotational equivalence for acceleration is alpha. So we end up having this equation right here. The sum of torque is equal to I, our moment of inertia or our rotational inertia, times your acceleration, your rotational acceleration, or alpha. So rotational inertia, again, depends on the shape of the object because all objects have different distributions of mass. Now, when we're looking at static equilibrium requires the sum of force and the sum of torque to equal zero. So this is really important. When you have static equilibrium, you have the sum of force and the sum of torque equals zero. Sum of force equals zero and sum of torque equals zero. Now, things that you need to recognize. First, objects with a larger rotational inertia are going to require more torque to start moving. But once it starts moving, it requires a larger torque or a larger friction to get it to stop moving. Objects with the same mass can have different rotational inertias and therefore can behave differently. And they have different rotational inertias because they have different shapes, because again, there's a different distribution of their mass. And then finally, changing the location of the axis of rotation will change the rotational inertia. Why is that? Well, because you're changing the distance between the rotation axis and where that mass is distributed. So when we're looking at torque, torque is going to be the analog or analogous to linear force. So it's important for you to recognize that torque equals rotational inertia or moment of inertia times angular acceleration. Okay, so let's take a look at a sample problem. It says a 20 Newton force is applied. So when you have your in-class practice problems, I really want you to practice underlining things. You really want to practice underlining or highlighting things just so that you know where you're getting your information from. So it says a 20 Newton force is applied to the edge of a hoop. That's going to be important because it tells us what type of rotational inertia we're going to end up dealing with. In a direction tangent to the loop to cause the hoop to rotate about an axis through its center. So we end up having our hoop. And imagine your pencil is sticking in the center of that hoop and you have that rotation right there in the center. Now the diameter is 30 centimeters. And its moment of inertia is 0.035 kilograms times meter squared. That's nice. It gives us our moment of inertia. So I is equal to 0.035 kilograms times meter squared. Okay. So it says, what is the angular acceleration experienced? Well, let's see. We have our sum of torque is equal to I alpha. Okay, awesome. Also, we know that torque is the same as force times radius sine theta, and that's equal to I alpha. Okay, and we're trying to solve for alpha. So our angular acceleration is equal to force times radius sine theta divided by I, or our moment of inertia. So we end up taking our force, which is 20 newtons, times our radius, which is 0.15, okay, times sine theta, and our theta is going to be 90 because you basically have your radius here, and then you have your force being applied this way, okay, because it's applied to the edge of the hoop. So you have sine 90 divided by 0.035. And that is going to end up giving you an angular acceleration in this case of 85.7 radians per second squared. Okay. So the main idea here, the main thing to remember is that linearly, when you're looking at Newton's second law, you have sum of force equals mass times acceleration. That's linear. And rotationally, sum of torque equals I alpha. Okay. So let's look at another question. We have question number 11 from your in-class practice problems, and it says a solid sphere or a solid uniformly weighted sphere in the diagram has a mass of 4.2 kilograms and a radius of 38 centimeters. A string is attached to the sphere and wrapped around the middle of the sphere and then begins pulling with a constant 30 Newton tension force that is tangent to the sphere's surface. If the sphere is at rest when the tension force begins acting, how much time is required? So, this is my question, is required for the sphere to reach an angular speed of 5.3 RPM. So, our omega final equals 5.3 revolutions per minute. And our omega initial equals 0. Now, what I want you to imagine here is think about like a yo-yo, but instead of a yo-yo, you have a ball, like a sphere, and you're pulling a string on the outside of that sphere. Okay, that's really what's happening. So you're starting from rest. It really is. I really think about it like a yo-yo, but you've got a perfectly spherical round yo-yo in this situation. Okay, so what are the things we need to consider? We need to consider our torque. We know that our torque is equal to I times alpha. We also know that our torque is equal to FR sine theta. But because it's at a perfect 90-degree angle to the radius, we're just going to use that our torque is going to be 30 newtons times our radius, which is going to be 0.38 meters. Okay, and that's going to end up giving me that my torque is equal to 11.4 newtons times meter. Okay, another thing that I need to look at is I need to figure out what my I is, what my rotational inertia is. Because I have a sphere, for a sphere, okay, this is for a sphere, it's 2/5 mr squared. So 2/5 mr squared. So I have 2/5 times 4.2 kilograms times r, which is 0.38 meters, squared. Now, if you're asking, where did I get that equation? You can look in your textbook for that equation, or you can go back to these notes. But also, your equations are going to end up being in your textbook as well. And those equations are on page 208 if you're wondering where your rotational inertia values are. So this is going to give me a rotational inertia of 0.243. And that's going to be in kilograms times meters squared. So I've got different values. I have my torque is here. I have my rotational inertia. And so now I can solve for my angular acceleration. And why do I care about that? Well, because it's accelerating and it's going from 0 to 5.3 revolutions per minute, 0 to 5.3 revolutions per minute. And we want to figure out how much time it takes for that to happen. So our alpha is equal to torque divided by rotational inertia. So that's going to end up giving me 11.4 newtons times meters divided by 0.243 kilograms times meter squared. So that's going to give me a value of 46.9 radians per second squared. Okay. Now I'm going to use that value and I'm going to look at, so what do I know? I know omega equals omega initial plus alpha times time. And I know omega initial equals 0. So what's my omega final? Because I know omega equals alpha times time. So time is equal to my omega final divided by alpha. Okay. And let's see what my omega final is. So over here on the left-hand side, I'm going to go ahead and figure that out. That's going to be equal to 5 revolutions per minute, or 5.3 revolutions per minute. So if I go ahead and I convert that, I have 2 pi radians for, and then I have per 1 revolution, and 1 minute is 60 seconds. So I end up getting that value is 0.555 radians per second. So I do 0.555 divided by 40, divided by my 46.9, and it's going to take me, I mean, that's a really small value. It's going to take me 0.012 seconds for me to go from 0 to 5.3 revolutions per minute. Now, our last question for today, we're dealing with a thin rod. And this is a very common question that you would see in AP. The College Board really likes to ask questions with moment of inertia and torque and rotational momentum and all of that dealing with rods. So we have a 2.3 kilogram thin rod that is 50 centimeters long, is free to rotate around an axis through one end as shown in the given top view diagram. So here's our axis of rotation. Okay. The rod is initially at rest when a force F starts acting at the center of the rod in a direction perpendicular to the rod, and the force's direction constantly changes to rotate along the rod. With the force F acting, the rod rotates through an angle of 24 radians. Okay. So that's going to be my theta, and reaching a final angular speed of 30 radians per second. So our omega final is going to be 30 radians per second. When the force stops acting, the rod slows under the influence of frictional torque that slows the rod to a stop after 5 seconds. So to a stop, my omega final here equals 0, and that takes 5 seconds from the first time that F stops. Calculate the magnitude of the force. Okay, so there are a couple of things that I need to look at. I need to look at the speeding up process, and then I need to look at the slowing down process. Okay, so what happens here? Well, I also need to look at my rotational inertia. My rotational inertia for a rod is 1/3 mL squared. That's the mass of the rod times the length of the rod. And that's going to end up giving me, because I have a 50 centimeter rod, so it's 1/3, 2.3.50 squared. That's going to end up giving me a value of 0.192 kilograms times meter squared. Okay. So I need to look at what's the speeding up process and what's the slowing down process. So in this case, I have my sum of my torque equals I alpha. Okay. And what is the sum of my torque? Well, the sum of my torque, I have two things. We've already been told that there's friction acting in this system. We've already been told that there's friction acting in the system. And then we also are looking at this in terms of we have the torque applied by the force. So we have the torque of our force minus the torque of friction is equal to I alpha. And this is my speeding up process. And then I have my slowing down process. My slowing down process, I am only looking at my torque due to friction, right? my torque due to friction is my moment of inertia times alpha. Well, how do I figure out what my alpha is in this situation? Well, I'm going from my 30 radians per second to 0 radians per second in 5 seconds. So my alpha in this case is going to end up being 30, or actually it's going to be 0 because that's my final, minus 30 divided by 5 seconds. And then my rotational inertia is 0.192 kilograms times meters squared. Okay. So my torque of friction, my torque due to friction is 1.15 newtons times meters. Now recognize my torque due to friction is not changing. So I can go ahead and plug this value right here into my torque of friction. Okay. Because again, let's look back at the question. What are we solving? We're solving for force. Okay. So we know that the force applied is, and then times 0.25 because it's being applied at in the center. So times 0.25 minus my frictional force is equal to my moment of inertia, which is 0.192 kilograms times meters squared, times my alpha of my speeding up, my angular acceleration speeding up. Well, let's look at that. What's my final? My final is going to end up being 30. Okay, and I don't know anything else other than my my rotations. So I have 24 radians. So I need to solve for this. Okay. Alpha in this case, if I think about it, I have omega squared equals omega initial squared plus 2 alpha theta. Okay, so alpha is going to be equal to, because my omega initial is 0, omega squared divided by 2 theta. And that's going to end up giving me a value of, so I have omega is 30 squared divided by 2 times 24. And that's going to end up giving me a value of 18.8. Radians per second squared. Okay. And when I go ahead and plug everything in here, I end up solving for my force, and my force is equal to 19 newtons. Okay, this is definitely a problem that you might need to go back over because it's a very detailed, long problem. So let me go through it real quick. You have this rod and you're applying a force. That force causes that rod to accelerate. It accelerates at a rate of 18.8 radians per second squared. And I get that by figuring out how many radians it goes through, and I have my final velocity and my initial velocity. So I figured 18.8 radians per second squared. Now, if I stop my force stops acting, my rod slows down eventually. And it slows down because there's some kind of friction. There's friction acting in the hinge, which is causing the rod to slow down. Well, the friction was already acting there because it's the friction, it's the kinetic friction, it's the friction from that motion. Okay. So when I find that friction, I'm applying it over the speeding up, the accelerating of the rod, but then I'm also going to apply it to, that's what's causing it to slow down. Okay. So I kind of had to work backwards a little bit to understand, to figure out what the friction is, and then plug the friction into my speeding up situation. Okay. Hopefully this is helpful. I know that it's a lot to get your head around. Make sure that you reach out and ask questions as you need them.